let me thank the colleague at IIT Madras for the opportunity, okay, to share some of the things that I feel like together we can learn, and so thanks to them. And hopefully after lunch all of you are awake. And so in this session, so there are two sessions will be taken care of by me with the help of my colleague here. But this session will be the lecture one, and the next session will be you have to do some kind of hands-ons. Okay. So roughly this sessions, although it is for 1.5 hours, so maybe it will 1 hour. Let's see how it goes. Okay. So in this session, so you had lectures starting from Monday, right? And you were having several lectures by giants in our field, like Professor Potim Chatraj, Professor Manoj Harbala, Professor Saurabh, and all, right? And let's see how you are able to connect what I'm going to talk. So these presentations, it won't be too much of mathematics rich, right? But still something will be there. I hope you will be able to understand. If something is not clear, so just pause me. And this looks like a classroom kind of interactions. So hopefully it will go well. And more like it will be some research components that we have done something along with some other expert who have contributed to the field. I will showcase so that you appreciate what method I'm going to talk about, how that is going to take care of certain challenging problem, particularly related to the excited states. Okay. So with that background, so the plan is basically why we are worried about the excited state. Probably for this audience it is not required, but for the completeness purpose I'll talk about it. And after that, how do you model those excited states? Okay. So what are the electronic structure methods till date available? Some not history. Already you had a good history starting from 1930, right? Hartree-Fock, or before that the Schrodinger, Hartree-Fock, then Weinberg-Kohn, and the Kohn-Sham equation 1965 you had. And yesterday also you had a great talk by my colleague Professor Bangshi, right? So on linear response to DFT. So we'll little bit touch upon it, and hopefully you'll be able to connect. And then we'll see how that method ultimately is giving you some reliable description of the excited electronic states. So with that background, let me just move forward. So my slides are a bit rich, so I will stop in each slide for some times. You can look at if there is some discrepancies or something you are not following, just let me know. Okay. And I also request my colleague Professor Bangshi is there, Somen is there, Professor Nishant Nare is there. You can add, to clarify or anything whenever you feel like, right? We are all in the same room. So let's move on. So how do I move? This one only, right? This one only, right? Or I should use. Batteries are not there. Okay. It's working. So I think this is mostly I verbally, talk about. The plan is basically look at the excited states and the modeling aspect, and few case studies we'll look at, and we'll see with that case studies how you understand the content. Okay. So basically when you talked about the excited state, you look at the excitons, right? And I classify the excitons are basically two classes, like a charge excitons and bound excitons, which are relevant for the excited state modeling. Under charge excitons, here I mean to say, like you take out one electron from the systems, you ionize the systems, is essentially the ionization energy or ionization potential, right? Or you add one electron if system has low lying, bound some empty states, right? So that will be able to accommodate that electron. So this is referring to the electron affinity. In the literature, you have also one class of excitons like trions, right? So they are also charge excitons. Here I am not talking about the trions. Here is basically typically the charge excitons are IP and EA, ionization potential, electron affinity, right? And if you look at IP and EA, they are not conserving the number of electrons. You had, let's say, n number of electrons, you are having n minus 1 or n plus 1, depending on what process you have. Then other set of excitons, what you have on the right hand side is the bound excitons. and this is basically you are creating a electron hole pair within the systems with some time dependent perturbations, time dependent electric field. So these are bound excitons, charge neutral. So you need to care for electron and hole interaction within the system itself, because system is not destroyed, system is still having the same number of electron preserved. And typically, you know, in linear spectroscopy or nonlinear spectroscopy, we look at this kind of bound excitons typically, right? You visual spectroscopy or you do ultrafast spectroscopy, we deal with optical excitons. And then we talk about the optical gap, right? So where is basically typically the lowest, you know, allowed optical excitons, excited state energies, we say optical gap. And the left hand side, you see on schematic diagram I have, this is typically if you have a two-level system, let's say HOMO, LUMO, HOMO and LUMO, the terminology you are familiar, or you can have valence band and conduction band. The two-level states, the gap between these states is basically what is known as band gap or fundamental gap. Literally, you define the fundamental gap or band gap is like IP plus EA, and again the IP minus IP plus EA or IP minus EA depending on how you define the electron affinity, whether this is anion minus neutral or neutral minus anion, depending on you need to take care of the sign. So this is what is the fundamental gap in the systems. And what you typically read in the literature is like a HOMO-LUMO gap. We call that is like an electronic gap. And essence, if you have an exact theory, right? So HOMO-LUMO gap and fundamental gap, they should map. Okay, if you have an exact theory. So, and in the optical gap, you see, since you are having a bound excitons, you have some sort of Coulomb interaction between excited hole and electrons, right? So that needs to be taken into account. That's why you see for these two-level systems, the optical gap at best will be equal to fundamental gap. Otherwise, it will be less than, right? Provided you are having these two-level quantum systems. And then this is basically where these are the things are very important, is basically, you know, the excitons once you create, if you can dissociate, you can have like in photovoltaics applications, or you can do some redox process at the excited electronic states, right? So these are the process can be, you know, looked at with the help of excitons, right? And then you can have also the in pigment industries, you can have also the recombination of excited hole and electron, and you can have, you know, applications in, you know, dyes industry as well as in organic light emitting diode. So now whatever is there in this slide, whatever I talked about, is this content clear? This is connecting with your spectroscopic knowledge, either in master's level or in undergraduate level, or whatever research some of you are doing, you should be able to connect. This is just very fundamental basic things. Yeah. What is it? This one is basically what I am referring, the electron hole mounted. This is look at the cartoon. You are sitting on the chair, and because of the excitons you are going out. So it's basically electron goes and holes created. So what is the Coulomb interactions between that electron and hole that we call exciton binding energy. Okay. So the fundamental gap and optical gap in a two-level systems are differed by exciton binding energy. If you are dealing with inorganic materials, inorganic systems, typically the exciton binding energy is very small. And inorganic chemist or materials physicist, they would refer to, okay, band gap, optical gap, all are essentially same. They are not essentially same. They will be same if you are having the exciton binding energy is very small. But as a chemist, mostly we deal with some kind of organic molecule. If you are dealing with organic or organic inorganic hybrid materials, the exciton binding energy is quite high, like 0.5 to 1 electron volt also you can have, okay, depending on the system. So you need to care for this exciton binding energy. Okay. Yeah. Mm-hmm. Yeah, so it should be like in optical gap if you are mapping with that invisible spectrum, right? Now the, you know, determination of optical gap, there are different ways, you know. So experimental colleagues will use, they will take the slope, the tangent where it is, you know, crossing, is right. So that is how they calculate the optical gap. Fine. But if you are interested for the fundamental gap, right, one should do the photoelectron spectroscopy. Okay, to get the ionization energy, or inverse photoelectron spectroscopy to get the electron affinity. Then you will have access to experimentally the fundamental gap. But if you do the optical spectroscopic, visual spectroscopic, so you have access to optical gap. E, it's electronic band gap, a fundamental gap, or whatever you call. This is gap, but you don't have the interaction between quasi-hole and quasi-electron that you have created in the systems. Okay. And our inorganic chemists, they do cyclic voltammetry also. So through cyclic voltammetry also you can get access to that IP and EA, okay, with respect to some standard, reference electrode, based on the electrode potential. Fine. Everything is fine in this slide. I have few slides, so I will pause. You ensure that contents are clear and then you refer, okay. Now, these are the things probably I will omit. These are all places where these excited states, makes huge contributions. I mean, modeling excited states, looking at the excited states. Either you look at the optoelectronics, like you have TADF, right, or blue emitters, or up conversions. You look at the photovoltaics I talk about. You look at the photosensitization, right? You use on chromophore as a sensitizer, and you have also the photocatalysis, right? Lot of photo-oxidations or reduction processes are happening at the excited electron states. So if you are interested to model all these are all few of them, but there are many, right? So this is several of them can be, if you are looking at, so we need to worry about this excited state modeling, right? So now, let's say you have a atom or molecule in isolated form, in vacuum. Sometimes in literature we call a gas phase, systems. Gas phase doesn't mean that your system is in presence of argon or some other gases. Gas phase means is essentially a vacuum, okay. So if you have, typically the gap is basically IP plus A or homolumo gap, fundamental gap. But if that system is immersed into an condensed phase, let's say a molecule is present in condensed phase, right? So what happens? The whole states, homos or valence band, they refer to the whole state. Due to the electrostatic polarization, that will be pushed off in energy. This is the energy axis. And the electron states, the empty states, where your electron goes, that electron states will be pushed down by some amount of polarization energy P, and you can calculate analytically what will be the polarization energy depending on what is the size of that molecule, as well as what is the dielectric constant of the medium. Analytically you can calculate. There are expressions in the literature like E square over R times 1 minus 1 over epsilon. So considering a spherical cavity and you are charging, you are adding a hole or electron, you can calculate. So what I mean to say, whatever the gap we talk about in vacuum, you need to take care of this polarization effect when you are talking about the gap in condensed phase. And this is known in the literature is like kind of fundamental gap renormalization or band gap renormalization due to dielectric of the medium. It doesn't have the contribution due to the phonon renormalization. Typically, the phonon renormalization will be much, much smaller than the renormalization caused by the electronic polarization. So whenever we are mapping with some experimental condensed phase studies, we need to take into account. Just doing the calculation in vacuum doesn't make sense, right? And what I mentioned, this PES stands for photoelectron spectroscopy or inverse photoelectron spectroscopy, can be used to probe this IP or occupied states and unoccupied states experimentally, okay. So what is interest is basically for modeling all these things, we need to have this quasi-particle wave function and energies, right? In the previous talk, you talk about that quantum orbital energies, right? If I consider those are quasi-particle states representing, those are the wave function and energies. No, here. Yeah, so the phonon-driven renormalizations are very, very small. Dielectric-driven renormalization will be of the order of 1 electron volt, like 0.51. But the phonon will be, like 100 times smaller. That's why one can neglect, but if you want to calculate, one can calculate, okay. So recently, I think some of you know Professor Wagmare from JNCSR. So they have done some work on, multifarious systems, the impact of the phonon contribution to the band gap renormalization. But the maximum contribution comes from the dielectric of the medium. If your dielectric constant is quite high, let's say you are working with zinc oxide, or some systems where you are having so iron nitrides and all, your dielectric constant is quite high. This is going to be very large. Even if silicon, you take the bulk silicon, dielectric constant is quite high, is about 12, right? Fine here. So is basically these states are, I am referring here like a quasi-particle states, okay? And the quasi-particle states, when I talk about, definitely it has eigenfunction, eigenvalues. That's what I am referring here. Okay, clear this slide? The next slide. This is, I briefly referred in the introduction, is basically in the optical absorption. You are creating a bound excitons, right? So in addition to these levels, you also need to capture this exciton binding energy, because you have the hole and electron, the quasi hole and electrons are created within the system. So you need to take into account that hole and electron interaction. So that is what I have mentioned, the quasi electron and hole interaction should be also accurately captured if you are looking at excitons in a systems where exciton binding energies are considerable, right? Typically the bulk silicon, the exciton binding energy is very small. If you look at the band gap is reported like 1.14 electron volt, or the direct band gap is 2.45 roughly electron volt, right? So for that the band gap and optical gap will be close. But if you are taking one simple molecule, let's say a benzene molecule or some organic chromophore, the exciton binding energies are going to be quite high. So that one needs to be worried about. So as a chemist, we always play with molecules, right? And functionalize it so that you can tune the band gap, optical gap of the systems, right? So here the quasi hole and electron interaction should be captured well. We have sophisticated experimental tool. We have sophisticated experimental tool to capture. Now in theory we should be able to capture it. Then you will get the reliable description. Fine in this slide. Let's move on. Then the quantities of interest in our hand, quasi-particle states, both eigenstates, eigenvalues, right? On top of that, quasi-electron hole interaction to describe excited states, right? And the available methods, in the first day, you had a great talk. I could not join, but couple cluster method was described, right? Discussed by Professor Saurabh, and these are called ab initio method. Okay, typically I meant to say you explicitly deal with wave function, many body wave function. Wave function based theory is basically ab initio. Okay, still in the literature you will find like ab initio density functional theory we say. Okay, but in the chemistry domain, if you talk to a professor quantum chemist, the ab initio they mean to say is basically go and deal with wave function. Here you'd say first principle density functional theory. That is how what I learned from the community interacting. This wording is, but in the literature mixed nomenclatures are there. People are also writing ab initio density functional theory or first principle density functional theory, right? So these are the post Hartree-Fock based methods. So you learn Hartree-Fock theory, there is no correlation, but the theory is fully self-interaction free. I mean, few full exchange is there, no correlations, right? So to take care of the correlation, you have some, in couple cluster method, you have exponential answers, right? You have a cluster operator to take care of the higher order excitons, right? And equation of motion couple cluster is going to give you the excited state energies. But these are very good method. You have to converge the calculation, but limited with the system size, right? Still, we do some calculation to benchmark, but if you are having large system size, we look for some alternative method, right? So alternative method is basically, physicists would love to choose, okay, the GW BSc. So here GW is basically the Green's function based method, and what you do is basically you look at this kind of one particle Dyson equation. So this is like your kinetic energy term, right? And the next term is basically the external potential created by the nuclei, and this is the Hartree. Already you looked at Professor Manoj Harbala's talk, also Professor Pratim Chattopadhyay, all. I mean, this morning also we had a talk, great talk by Professor Nishant Nair also, had all these expressions, right? So what I want to address, this one you look at. There you had some exchange correlation, right? Here what you are having, highly non-linear, non-local, the self-energy operator, energy dependent. That you need to compute within some method. So this is basically taking care of the many body term. This is basically many body effects are taken care by the self energy term. And whatever the energy you get, we call quasi-particle energies, and the phi, whatever you get, is a quasi-particle states. So in the heading, GW approximation, the self energy, sigma is calculated like IGW. So G, if you want to calculate G requires access to the Hamiltonian in a given basis as well as the eigenvalues, and if the bases are not orthonormal, you have to take care of the S. So typically the simple form of G, you can think about the Green's function is like 1 over ES minus, you have the Hamiltonian operator and some small number eta. So this is how the Green's function. So this is what? This is the eigenvalue matrix. Okay. This one is overlap matrix. Even if you know molecular orbital theory, Huckel molecular orbital theory, we come across and all the things, right? The S is the overlap matrix, and this one is the Hamiltonian matrix written the given basis that you have. So in order to calculate this, you need all this. On top of that, you have the W. Now W is referring here is basically, if you look at the expression, which is basically the more complicated part, is like inverse dielectric matrix times the Baer-Coulomb potential. And the GW method is expensive. The reason is basically sitting here, the inversion of the dielectric matrix, and the dielectric matrix has to be calculated also. And that requires the sum over states. You have occupied and unoccupied. There is a SOS sum over states method. This is the expensive part. So once you calculate the screen Coulomb interaction, you can define the self energy. And once you have the self energy, either you can solve, but the practical GW, whatever the practical way of using GW is basically you get reasonably good like quantum eigenstates and do some kind of first order corrections. So what I mean to say, you do the quantum DFT, whatever like quantum, you get all these quantum orbitals. You get these quantum orbitals. So that means the set of orbital energies you get as well as the orbital itself. These are all 1 electrons quantum states. And then what you do, since they are not appropriate quasi-particles, so whatever is lacked, that you treat using perturbation theory. So means to say, if you have a chosen like this, and what you get, like by solving this one, let's say these are all 0th order, okay, 0th order eigenstates, quantum states, okay. This one, yeah, quantum equation. Is it? No, this is not typical Hamiltonian. This is exactly like in Hartree-Fock also the Fock operator. No. Yeah, thank you, Professor. So what you have access to this one, right? And you need to have some kind of correction. That correction, how do you? So you know the first order perturbation theory. If you have the operator, an operator is what? This is basically the operator. Here, the self energy you get it from here, and exchange correlation energy based on LDA or GGA or hybrid, whatever level you will have, based on that you will get the quality. The differences will be minimized. Okay, if your VXC is exactly like non-local energy dependent, if you are able to get, they are supposed to be same. There will be no correction. So this is the correction what you do. Again, this is basically the 0th order state. And what we do typically in classroom, this is the first order energy correction, because for nth order energy correction, I just need n minus 1th order quantities, right? So this is how in practice the GW works. You have the quantum, or even if you start with any main field approach, you get access to these guys, and then perturbatively, using first order perturbation theory, you get correction to the energies. And if you are interested to update these orbitals, and you have also the first order correction to the wave function, the expression is known, is well established, right? So you can get it. But that is where the cell consistent GW enters. So I believe there is a talk either tomorrow or day after tomorrow, GW, particularly for the molecules, will be there more. Hopefully you will be learning more. But what I want to address, the quality of these states, the quality will dictate what will be the quasi-particle spectrum. And that quality of these states again depends on that whatever the many quantum exchange correlation potential, how you are approximating the many body interactions there. Okay. So this is quite expensive. Typically, if you look at in the physics, solid state simulation, particularly for semiconductor physics. So they have been using, to get the excitonic picture of semiconductors reliably. Okay, in this slide. The answer is yes, from wherever you have access to the quantum state you access, but ensure that your this operator, right? This operator is like a small perturbation because I am truncating the first order correction only. I am not going for the higher order correction. So if the difference is small, this is essentially in my perturbation theory, H naught plus some lambda H prime, right? And that H prime is basically this difference, right? So now if these states itself are quite good, you are getting from the wave function based theory. Typically from the wave function based theory, you get many body quantum states itself, right? So if you simply do the Hartree-Fock theory, that is the interacting systems, unlike the quantum picture, right? Yeah, this is basically the single particle basis here. So whatever the energy we are having, these are all quasi particle which are basically single particle itself. Yeah, but for wave function based theory, if you have access to the many body, see, if you have the single particle, you construct the n electron slatter determinant. That is itself your many body wave functions, right? But the question that you have asked, like, can I use, because already you are having good theory there, right? This method is recommended for the systems where you are unable to do the wave function based theory. Okay. And for solid, particularly for periodic system, this morning you heard the talk by Professor Nishant Nair. If you have a solid, and for that, this is a gold standard method. I am saying the gold standard, again, the gold standard depends on the initial states. That is something referred in the literature, starting point dependence of quasi-particle spectrum. Okay. And there are some approaches, you can have eigenvalue self-consistency. You keep updating the eigenvalues, still retaining this mean field type quantum states in your hand. Or you can do both. You can keep updating eigenvalues as well as eigenfunction. That is a fully self-consistent, which is very expensive one. So in the literature, you will find like eigenvalue self-consistency, they refer as partially self-consistent GW, right? I will have some result with call something is there G naught W naught. This is in the literature they have named. So that means a single shot. You get access to this from your SCF calculations, DFT calculations, and do correction using first order perturbation theory and what is known as G0 W0. Okay, the single shot GW. Okay. Epsilon inverse is not going to be, you will be having just a bare potential then, if it is unit. That will be like, that your Hartree exchange, that's it. But essentially that epsilon captures that inhomogeneity of the systems. Okay. Fine. Then where this is something, yesterday you had a great talk by Vangshi as well as Professor Manoj Harmola also, talk about that he is going to address tomorrow something derivative discontinuity. I will just briefly touch upon so that you get the essence of this talk, and then you will have more clarity, and sir can add here also because this is a very interactive way of learning. Okay. So I request Professor Gautam Chatterjee, Professor Barbala, if you want to add, you can add here. So let me just go ahead. This is what typical is basically the 1965 practical implementation of the Hohenberg-Kohn theorem, right? In Hohenberg-Kohn theorem, the two things are there. The potential is connected with the density within an additive constant. The next one is the variational minimization. From where you get this kind of one electron Schrodinger like quantum equation. So here all these terms are known to you. This one is basically in my terminology because I have taken from some reference. I did not change it to external potential. This is essentially the same potential exerted by the nuclei. So this one in quantum formalism, it is basically a local potential. Okay, it's a multiplicative potential. So using this quantum formalism in 1970 itself, that bulk modulus, cohesive energies, they were quite good, but the band gap problem was there. The quasi-particle gap problem was there. For molecules, we are interested in high energy quantum, like localized quantum state, Rydberg quantum states. Or some, if you are dealing with some kind of organic molecules, donor accepted type, you will be having some kind of charge transfer state. There is a huge problem. If you look at all these quantities, and particularly the essence of this excited state modeling, are essentially the eigenvalue derived quantities. It's not density derived quantities. So it's basically we are dependent on the eigen spectrum, right? It's not like we are interested for forces or electric dipole that can be derived from the total density. Total density, total energy was good with local potential. But these are the quantities are related to eigenvalues. So people have, even long back, I mean, this is the article I have read, Purdue's very good article, but there are many other articles, right? Before I was a PhD student itself, like everybody, DFT is a band gap problem. I did not understand what is the band gap problem at that point of time, okay? But there are a lot of stocks and all from there, slowly, we develop the learning. I see. I see. I see. I see. And there is one also review article like bird's eye view. I mean, for the beginners to understand that I think Karplas, the bird's eye view in density functional theory also. Okay, maybe that is one article, review article, very good to start with actually. So what I refer here, this is you look at. So Professor Manoj Harbolla yesterday was right. If you are using quantum DFT, right? Right. So that Koopman's analog of this DFT analog of Koopman theorem, that the HOMO energy will be equal to the negative of IP, or you can write IP equal to negative of HOMO. This is going to be valid for an exact theory. And then this one you look at is that R tends to very large, it should be like asymptotically decay, right? This 1 over R dependency. But if you are having some LDA, GGA type potential, which is basically you have looked at yesterday's talk, it is basically exponentially decay potential, right? So these are the three quantities, and this is delta means the derivative discontinuity. What is the derivative discontinuity? Is basically if you plot the total energy as a function of electron number, then the energy, it can be shown that from the ensemble generalization of quantum DFT itself, you can show that it should follow the piecewise linearity condition for exact theory. So that means this is a straight line and this is another one straight line. And slope of these lines are essentially is basically ionization energy and electron affinity. So if you take the derivative of these two straight line, you have the discontinuity and in the exchange correlation potential, right? Because the energy derivative with respect to the electron density is essentially the potential. So there will be a jump at the integer number. But if you use LDA and GGA, that there will be some derivative discontinuity will be missed. This is something you read in the literature called missing derivative discontinuity. Is this clear what I am referring? The energy versus N, if it is like this kind of linear, piecewise linearity condition is there. If you take the derivative, what you will get? The slope will come, and this slope and this slope is going to be different. There will be a jump. But if you are able to take care in your exchange correlation functional this discontinuity inside, then this IP minus A, right, this fundamental gap will be exactly equal to that HOMO-LUMO gap. Otherwise, there will be a difference. Okay. So here there are a lot of functionals, and yesterday also you had talked by Prosenjit, Professor Prosenjit, right? There are 18 constants, right? He discussed thoroughly, right? So some of these functionals are having this convexity, concavity problem. LDA, GGA, you will be having, convex. If you are having some kind of, some Fock exchange, you will be having convex. So this problem will come. But if you have an exact theory, you are having a linearity problem.
Actually, I should tell you, this is a general caution for people who are trying to work on conceptual DFT. You know that whether it is capture potential or hardness, you have to find out del E del N or del 2E del N2. If it is not a continuous function, then how can you get the derivatives? That's a big question in conceptual DFT. So Professor Parr and others, they had shown that if you go to a corresponding finite temperature formula, you can get a continuous function where you will find out the difference. So this is the finite temperature extension of this and that gives you the whole of this conceptual DFT is based on the derivative. And if you don't have a continuous function, you cannot find out the derivative. They don't exist.
Good, thank you. So whatever is here is clear. Any questions? Whatever is shown in this slide. Sorry. Yeah.
This is one point which has to be clearly understood.
Yeah. No, I'm going slowly so that later on you should not. Okay, what are the languages there? You have promised that you'll do that. Okay. So you have sir with us. So we'll have in depth. Okay. So in this slide, okay, what I have, this is basically in 1996 by Seidel. This is basically called generalized quantum equations, where you have a non-local orbital dependent operator that includes some kind of exchange, right? And then remainder part is basically local type of potential. This is like an eigenvalue problem. This is still we are in one electron picture only. But only thing is that now we have some kind of Fock exchange. I won't say Fock exchange. In the literature, I see they use smartly Fock-like exchange just to differ from the Fock exchange in the sense that the exchange is calculated using still the quantum orbitals. Okay. So the exchange energy, it's Fock-like exact exchange. The term is not Fock exchange. The reason is that we are not using Hartree-Fock spin orbital. Okay. These are all still quantum orbital. So that allows to add some fraction of non-local exchange, right? And then you need to have some complementary exchange in order to, this complementary exchange come from LDA or GGA, right? Semi-local exchange, and then as such you are having the semi-local correlations. So this is basically the generalized, within the generalized quantum picture. So whatever the B3 leaf, PB naught, typically you read in the literature article, they are basically following this formalism. These are called global hybrid. So over the entire interelectronic coordinate, that R1 minus R2 you can think about, over the interelectronic coordinate, you have same amount of Fock exchange, and this can be understood using adiabatic connection method itself, ACM method. Okay. So here I have written what you have already. So some amount of like PB naught is basically 0.25 you add as AX, like 25% Fock like exact exchange is mixed with 75% PBE exchange. In B3 leaf you are having, instead of 25 you are having some about 20, exactly 19% of Fock exchange mixed with 80% of Beке exchange. So B3 leaf, yes, all these exchange, this is not Fock exchange, Fock like exchange. Okay, this is how we refer. Okay, fine here. So these two functional that you commonly use, particularly more than your theoretical chemist or computational chemist, experimental colleagues are using still today. That's why the citation, if you look at it, has crossed more than 80,000. Okay, this is Axel Bekke. So this has gone because most of our experimental colleagues, they are using B3 leaf, whatever they do. Okay, but this functional is good for structural properties. If you are interested for modes, structural parameters, this functional is, both functionals are good. More parameters are hidden here. So PB naught is more better because it is more generic, less parameters. Okay, but just keep this in mind. This is still, we have the addition of the Fock exchange throughout entire range. Okay, that's why this is called global hybrid. The reason I am saying, because my talk should focus on range separated hybrid, I am just bringing you what is the range separation there. 1 second. So here is basically, that was time independent quantum. You can generalize this one in time dependent quantum equation using local potential as well as the non-local potential, right? So this is basically the time dependent generalized quantum equations, okay. And this is the non-local part is there. I was feeling that did I copy the same thing, but no. So some of these difference is there. So the potential should have non-locality. So that is coming through Fock-like exchange. Now something I am connecting with Professor Bongsi's talk yesterday. We are talking about, TDDFT. Are we solving these things? Essentially, in today's quantum chemistry code, either Gaussian, Orca, or NWChem, whatever you use, we don't solve these things. What we solve is basically the linear response TDDFT. Okay. In linear response TDDFT, what you do, you considered your density is perturbed linearly with respect to the external potential, changes in external potential. So that means the del Ni, right, can be written is like a N naught plus del Ni. That del Ni is basically some kind of first order density correction due to the external potential V del V xt. Okay. So now what is this mapping is there? If I trust that Runge-Gus theorem, right, 1984, what it says, the mapping of time dependent density with time dependent potential with a additive time dependent constant, right. The first statement is basically the mapping of time dependent density with time dependent potential with an additive constant, time dependent constant, no spatial dependence, only time dependent constant. In Weinberg-Kohn theorem, first, if you relate, the ground state density maps with potential with the additive constant, right? That is the difference. But in Runge-Gus theorem, we don't have the variational minimization. We don't have variational minimization. We need to define a quantum mechanical action function. The time evolution of that is basically, if you start with T0, what happens at T1. So we don't have variational minimization. That Professor Odin Chattaraj also yesterday, I learned he was also referring the same thing. Okay, there is no variational minimization. So here in practice, what you do, if you have an interacting systems, whatever the first order density change, I can map with a non-interacting quantum type equations. So this is also the same amount of density change should be there for the non-interacting case. If I hold this one true within the first order, correction, which is linear, okay, then you can derive this expression. What is this expression? This expression, yesterday's Bongsi's lecture, you had the del Ni can be written as like a chi times del V ext, right? So you can derive this chi. What is this chi? Chi is basically that density response function, or we call like dynamic polarizability. Sometimes people refers also susceptibility. Okay, this chi here, whatever is there, this chi function that depends on r prime and frequency can be written as summation over, let's say, kj, and you have some occupation fk. I'll explain, don't worry. Times, I'll just write what you have, phi k star r, phi j r, phi k star r prime, phi j r prime. This is in the numerator, and denominator what you have, the energy dependence, frequency dependence, then ek minus ej, and to take care of the singularity you add a small positive number. This is basically what I have written down is basically chi non-interacting. I will write like the dynamic polarizability or then response function for the non-interacting systems. Okay, so you are familiar with that S, quantum, that S is coming, that VKS, that S I am writing. So what is this? These are all occupation number of this quantum spin orbital. Okay, and these are all orbital energies, and this is basically the frequency. This is how the chi for the non-interacting systems you can calculate, right? And this equation you can get it from here itself. So this one is what? For the interacting systems, inverse of the chi function. This is what expression I have written, inverse of that for non-interacting system, the chi. And what is this quantity? This is something I will refer later, or it is here only. It's called Hartree kernel. You have come to know Hartree potential, like Hartree energy differentiation with respect to electron density, right? If you take one more differentiation, is basically called Hartree kernel. Same thing is basically what is written is the energy dependent non-local, the exchange correlation kernel. This is basically the first order differentiation of exchange correlation potential with respect to the electron density, or second order differentiation, here it is written, okay, with respect to exchange correlation energy. So that will come into picture. So what you do, you need to solve this chi inverse equal to 0 and get the pole of chi function. Those are the true excitation energies. What we get from our quantum chemistry code, linear response to DFT code. And the residues, that's going to give you the dipole oscillator strength, or some kind of, intensity of optical excitons. So pole and residues of these chi functions are connected with what we are looking at, like excitation energies, or that whether that excitations will be allowed or forbidden. But still, some codes are doing this one, but most of the codes today we use not this one. This, if you want to solve chi inverse equal to 0 in a coupled basis. When I say coupled basis, I am referring to Professor Bongsi's study. He was talking about the occupied unoccupied pair. You have m times m. That m is basically coming from how you write down the quantum orbital in terms of the basis function. Either you use Slater type basis or Gaussian type basis, you will be having a basis set, right? The number of basis functions will dictate the value of m, what he was referring, right? So depending on the number of electron in your systems, you have some occupied states, and rest are going to be unoccupied states. So in that, yeah, that's true. That's true. That's chi. Yeah. So you can write down in an occupied unoccupied orbital basis. That's why most of the code when you use, you get excited state. This is the energy, this is the oscillator strength, and now it is written like some orbital pair, their contribution to that state, right? So you will see that one from the hands-on sessions, what I am meaning here, okay? You will get to know. So what you do, if you transform that one and then Cassida, Amy Cassida has shown this problem can be mapped into a matrix. Solving this matrix, this is known as popularly Cassida matrix, where A matrix and B matrix elements are written like that. Again, whatever the matrix element I have written, there is no Fock exchange added. If you add the Fock exchange, then additional term will come. So this is still A and B matrix elements are written in terms of local type exchange correlation potential. If I have some amount of, let's say Cx amount of Fock exchange, I will be having additional term, okay? And what is the significance of X and Y? They are basically the whole electron and electron hole, that amplitude, okay, connected with excitation and de-excitations, okay. So in this Cassida formalism, for certain cases, particularly if you have a clean charge transfer state, or you want to model like triplet excited states, what you do, this coupling of the excitation and de-excitation, these elements are found to be 0, that can be neglected. So this matrix will be just transferred to like A vector omega that vector. So that is what is known in the literature. You are reading like TDA, Tam-Dankop approximation, where you neglect the coupling term between excitation and dx. The B matrix element will be not there. So it will just like X equal to some Wx. Okay. So that is the Tam-Dankop approximation is good for clean charge transfer state as well as the triplet excited state. So here what I have written down directly, that expression, we don't have the time dependency here, no memory dependency. Please note that when you do that from the action function, I did not talk about that action function depends on time as well as the initial state, because your system has to be at some t equal to t naught, some phi naught state. The dependency will be there, all these dependencies are gone. And what is known as adiabatic approximation. You don't have the energy dependency, you don't have the initial test dependency, and that is what we have in our most of the quantum chemistry code today when you do. So we don't have memory dependency, we don't have energy dependency in exchange correlation kernel. This is kernel. Okay? Is this clear, this slide? And there is a good book by Nempa Maitra. Okay, so these fundamentals of density functional theory, I would refer like this is like a Bible. I mean, there are a lot of authors. Gross is also there, right? So this is a Bible of time-dependent density functional theory, particularly the linear response part. You can go through it, and then some of the work done by Professor Leo Kronig at Weizmann. Okay, so you can look at this. Fine. Shall we move to the next slide? Are you following or not? At least to some extent you are following, right? Because you are doing some calculation, you should be able to map what I am doing actually. Okay. So now this slide, this ladder you have seen already, right? I am sure that whenever you heard DFT talk, this ladder is there. So you start with first rung LDA, then GGA. This PB is basically one functional under. So please note that LDA is basically a single functional, but GGA is like a class basket. Under that, different authors have given different functional. And if you are using any functional, typically we generally force the student go back and read that article. What was the need of that particular functional? It is just to adding in the basket, or something was required. That's why that functional was designed, and there will be some cross and crons. Both sides are there. We need to be aware. Not like that X author has used this one, I am using that. Okay, the blaming others is not good. Better to refer what is the pros and cons. So this one is basically the meta GGA, right? Meta GGA you got introduced, right? This is basically you are having the kinetic energy density also into the picture in addition to the gradient. And the fourth rung, right? Fourth rung is basically the hybrid functional, where you have some non-local exchange. It's like a global hybrid meta GGA, all are is basically in this rung, fourth rung of the Jacob's ladder. Okay, so this was required, this Fock exchange to take care of certain things, like the failure of all these things were addressed like this. So if you are in this rung, to some extent you are able to map, but still if you look at this 1 over R dependency, will be not able to capture with global hybrid, because global hybrid is going to give you the potential. How it will go? Some fraction divided by R. If you are using PB naught, it will be 0.25 by R. If you are using B3 leaf, 0.19 by R, unless you are changing that fraction of Fock-like exact exchange. So you are not getting this kind of asymptotic behavior. Then this class of functional, this is I am referring, this is a class of functional. This is called range separated hybrid. This is also falling in this rung, fourth rung only, because this is still hybrid. The cost is same. It's like a same class. So what you have done, this is basically, if you look at, go back, that time I was an undergraduate student, 2004. So Professor Chaturaj was referring, see, this is like work by student Inai et al, Heroth Grove. So what is, this is basically that Coulomb part, that exchange part, not that Coulomb. This is the Coulomb potential. So it's like an exchange part of that. You range split into a long range and short range. I'll explain this one. And range splitting is done through an error function. If you look at the error function, this is a function of gamma times R. So definitely from the functional form, you come to know that gamma must be inverse distance, right? Otherwise error function doesn't make sense, right? So that means gamma, if you have a large gamma, that means smaller interelectronic separation. If you have a smaller gamma, you are having large interelectronic separations, right? So gamma has a dimension of length inverse length. So this is basically the long range and this part is the short range, and the exchange correlation energy can be written like that. What is that? What we do in the hybrid, some amount of Fock like exchange you mixed in the short range. Let's say you have an interelectronic coordinate, and depending on the systems you have some gamma pointer, and you define this is my short range, this is my long range, how I am going to treat. And I required in the long range this 1 over R, and 1 over R is guaranteed for vacuum system. I mean molecule in vacuum is guaranteed by Fock exchange. So if I have full Fock exchange, 100% Fock exchange in the long range, then this is satisfied, right? So although in this functional, original demonstration, this functional, that the long range Fock exchange part was 65%. Please note that when you are reporting, like reviewers are asking, use long range corrected functional. If you are using CAM-based relief, it is not fully long range, because the long range part scaled like 0.65 over R, unless you are going and tuning that percentage. By default, it is 0.65 over R. Okay, there was a reason for them because they have done some kind of test set up there. They look at some atomization energy. For them, it was good. But for your case, if you are studying something where you required 1 over R, so 0.65 is not guided by the physics, right? Okay, and then the complementary amount of DFT exchange in the short range. And then this alpha plus beta is basically the total amount of long range. If alpha plus beta, which was considered by NI 0.65, instead of that we should consider 1, right? Then you will be having a full fork-like exchange in the long range. And complementary part, DFT exchange will be there, either LDO or GGA in the long range. And then full correlation, we don't do correlation range separation within this range separated class of hybrid functional. Fine. Now let's try to understand this. This is basically what I was referring, like how do you understand the hybrid formalism? This is what is the x-axis, the interelectronic separation. And then how 1 over R, the potential is scaled. So this is basically some alpha amount of fork-like exchange you are having, and if you set this DFT exchange in the long range, which Ni considered 0.65, so if you set this one 0, it's basically some fraction of exact exchange you are adding in the short range, right? Some fraction, not full. Some fraction you are adding, and complementary you are having some beta amount of, because alpha plus beta is 1, so beta will be 1 minus alpha. The complementary part will be DFT exchange, right? So this is basically how you understand that range separation answers within this class of functional. Is this clear? So whenever you are using this range separated hybrid, I have given 2 examples. One example from Martin Head-Gordon group, like omega b 97xd. The tag, if you put in quantum chemistry code, it will read what all these parameter. There will be some default parameters. The gamma value, some default value will be there, as well as the amount of short range exchange, and all these things will be there. And this is another one very nice functional from Professor John Hubbard group from Ohio State University. Okay, so this is also a long range corrected functional. Here is basically, instead of Becke, you use PBE correlation, which has been really optimized well for the exchange part. Yeah. So I apologize for that. I am repeating this exchange. We are calculating using quantum orbital, fork-like exact exchange, not fork exchange. Exact like. But in the literature, like fork-like exact exchange they refer, right? Commonly. Yeah. I'll talk about. That is the essence. Okay. It's fine. Now, if you look at this exchange correlation energy, there are some parameters, right? One parameter is definitely how do you set the pointer, gamma. We'll be touching. So that will come also. Okay, we'll touch. So that is going to the 5th rung. So this is 4th rung we are, and we'll go to the 5th rung also. Okay. So that alpha, as I said, the short range exchange, right? Fork-like exchange, or I may not be consistent with the wording, but I hope you understand what is the meaning of the alpha, like a fork-like exact exchange, okay, or exact-like fork exchange, you can say. And beta is basically the long-range part, gamma is the pointer. Okay. Now let's go to the next slide. This slide is fine? Not? It's clear or not? Clear, right? Yes. Yeah, this is basically the separating the exchange component of the Coulomb. So what we are doing, we are treating the exchange part only here. Error function we are using because we need to have the complementariness and smoothly varied potential. So error function guarantees, because if I have error function, the other part is complementary error function, right? This is 1 minus something. I need to have a smoothly varied potential form, and if I add up, I should get the complementariness, should be 1, right? The alpha is basically for this functional, Martin Head-Gordon, that original functional in 2008, okay, by Martin Head-Gordon. The alpha value, if I recall, it will be like 0.22, 22%, okay. That is the typical range of this alpha, 0.15 to 0.25. No, this is a long range connected functional. The alpha value is basically amount of fork like exchange added in the short range. That is the meaning. This is long range corrected, because in the long range what I have, if I set alpha plus beta equal to 1, I have full 1 over R dependency, right? And which I don't get from LDA or GGA or even with PB node or B3 lib. Okay, that is the spirit actually. The spirit is basically, okay, I take care of the long range separately, short range separately, and then I add it up. Okay. So now the question is basically all these parameters, either you have experimental data, you get it, and that's how, because initially the set of these functionals where the parameters have been given. There will be G1, G2, G3, G4 test set. Each set will be having of the order of hundreds of molecules, either atomization energy or some other properties, and they have optimized the value of what will be the pointer. Pointer means this gamma, or what will be the alpha. Alpha is typically is basically roughly 20%. And I would say, based on my own experience, if you are having states which are localized and delocalized in the valence orbital, when I say valence orbital, that means close to that Fermi energy. If you are having localized and delocalized, you must have some percentage of fork exchange added. Otherwise, there will be state will be reordered, and you will have garbage picture. Completely absurd picture you will have unless you add, and that is basically the spirit is not different from B3 leaf or PB naught. There knowingly or unknowingly you have some 20% of fork exchange, and the reason was, okay, I have to take care of the SIC, the self interaction correction. Okay, I mean not fully, at least to some extent I will be able to get rid of it, so that the overbinding, underbinding issues will be taken care. But here we are not talking about the overbinding or underbinding. You have the experimental structure you have got from somewhere, and then we are looking at some properties which are dependent on eigenvalues, eigenspectrum. Fine. Okay. Clear? I am spending more time. If you understand some problem related to that, you will be implementing there. Correct. That is one thing. At the same time, you also don't lose the control on the short range. Yeah. There is no long range, because that is a short range corrected hybrid. That function there is the short range corrected functional. You don't have the long range component, because in solid, to take care of that large system size, doing PB0 calculation is very difficult. And if you are doing range separation in solid, it's going to be very difficult. So long range part is I don't take care, because most of the effects are basically local because of the periodicity. So whatever the functional you are referring from the literature, HEC03 or HEC06, they are called short range corrected functional. So I don't have this part. Alpha plus beta, this is equal to 0. That part is not there. And that is good for periodic systems, solid state systems, and will be able to reasonably take care of the quasi-vertical band gap. But even if the HEC06, at each k point you have to calculate the fork like exchange. If you are doing gamma point calculation is fine, but if you have to get the electronic band structure, you need to go over a k path, and then it's very costly, right? But in like WASP code this morning, also Professor Nishandan was referring, you have PB not, but no one uses, because you will be not able to evaluate the exchange component in the long range. In my understanding, sir, I would say all the time we go and take the Hamiltonian depending on what is our interest, because problem should be in our hands, then you go how to solve it, not we have tools and then search for the problem. These are all these are all like properties and system dependent. It is, sir, it is coming from first principle analysis. I will demonstrate this one. We don't need to depend on the yeah.
Showing that it is fitting into your first principle. That's also postulate. not direct.
But I think this is like a chicken and egg problem, right? How you take? Yeah, yeah. Please, sir.
Initially, the artery fog and the DF density function approximations, they were mixed by using something called the adiabatic. Maybe I should write adiabatic approximation.
Mm-hmm.
Adiabatic approximation, and that gave what is called Becky's half and half. So
Yeah.
that gave half artery fog and half density function.
Yeah.
Half artery fog gives you long range, which is 1/2 1 over r.
Yeah.
Whenever you mix a fraction of artery fog, it will always give you fraction divided by r. On the other hand, so artery fog treats long range very well because exact artery fog gives you 1 over r. So the way to do is if I take the long range part and do a artery fog, that is, so long range part will always come out to be right, no matter what you do. The long range part far away goes as 1 over r, and if I do a artery fog, that's what it comes out. And short range part, then you can treat. And correlation effects anyway are short range.
Yeah.
So if you, for example, there's a whole history to it. So long range, short range separation actually comes from studying plasma oscillations in solids, so known as Bohm points theory, where the correlation was first calculated using separating Coulomb into short range and long range part and into short range part quite a bit. So it has a long history from 1960s. The other rationale for this has been that artery fog band gap always comes out to be roughly twice as much as the true band gap, and DFT band gaps always come out to be roughly half less.
Yeah.
So people thought if I mix artery fog and this, so the indications were from all over the place, but then it finally came out to be like this. That one could do it properly through adiabatic connection, and then also wanted to get the long range part. The other thing is the paper by Purdue and Zunger where they introduced self-interaction correction. And that self-interaction correction gave very good band gaps for particularly the inert gas solids. So it was also clear that if you improve self-interaction correction, you get good band gaps. And artery fog, so one thought if I do artery fog long range, it correct, so self-interaction correction come from long range and that will be corrected, so the band gaps will come out to be okay. So there are many rationales, but it was being done ab initio and with proper.
Yeah. That's true. Yeah.
Exactly what
Yeah. It's basically all at the business is basically the right amount of exchange and correlation overall the range. Okay, how do you take care of it? Exactly. Yeah. Roy Baer, real chronic and all. Yeah. Okay. So this slide is fine, right? So now thing is that one way to get alpha, beta, gamma by fitting to the experimental data. When I say fitting to the experimental data, some properties of a system you have that you get fitted using a set of alpha, beta, gamma, derive that functional and then whatever the properties you get. Okay, this is one way. But before I come how to get this alpha, beta, gamma, I just would like to trace this contribution from Lior chronic growth. Is basically what is this? This is basically that x-axis is the interelectronic distance, y-axis is basically that long range part, this alpha plus beta error function, and then this y-axis is basically the dotted line. This is the complementary part. Okay, so what we are doing, the impact of the alpha for a given pointer, given range separation parameter. On the right hand side, impact of gamma on a given Fock like exchange. So if you see what you see, the larger the alpha, typically if you have a large alpha, so what it means you are having more amount of Fock exchange in the short range, right? So that is what it's seen here. You go from 0 to 0.3, you got larger amount of Fock exchange. It's natural. This is just a pictorial demonstration what you do is 1 over R exchange splitting into long range and short range. And same complementary way the GGA component will be shown, right? And here you see if you have a larger gamma, the GGA is going to be more, like GGA contribution is more localized at a small. Larger gamma means your pointer is closer, it's the inverse distance, right? The GGA is going to be more localized in the short range. And here if you see, if your gamma is 0, essentially what it means is infinite, right? Right? What you are going is basically with this fixed amount of alpha, you are having a global hybrid. The entire range you have added alpha amount of Hawk exchange, right? And if you are having gamma equal to 0 on top of alpha equal to 0, right? Your pointer is full range, you are just having the semi-local type of exchange correlation, which is basically GGR. This is the limiting things, right? This is nicely shown in this pictorial representation. Now I'll come back to how do you do this alpha, beta, gamma, right? So particularly, if you look at in vacuum, when I say vacuum, this is an isolated molecule or molecule in gas phase. Instead of gas phase, I would prefer to say in vacuum. No one is there. Okay. So alpha plus beta should be 1. So the long range exchange should be full. Okay. And some amount of Hawk exchange, as I mentioned, if you are having some localized and delocalized state. Let's say you have a pi type of orbital, you have some non-bonding orbital. Their natures are different. Unless you use some amount of Hawk exchange in the short range, you will be not able to get the right order. So this alpha has been optimized using the piecewise linearity condition in one slide I showed. You can also demonstrate that one. NWChem quantum chemistry code allows you to get energy for n energy E as a function of n plus minus delta. Okay, you will get, and you can satisfy that one, and you can identify what will be the value of alpha. So based on this optimization, alpha is roughly about 0.2. Now depending on the code, that one functional omega b 97xd, I said one of your friend has asked 22% exchange, but Chai after 4 years of 2008 2012 they have published another one PCCP article. They have said, okay, I have to take care of little bit of non-local correlation for van der Waals type of interaction, what you refer like omega b 97xd3, in order to take care of that non-local van der Waals, because van der Waals interaction is basically a non-local correlation. That to modify it, their group had to modify also the exchange amount. That brings down to 0.19 instead of 0.22. So these are the, although you use the keyword, I would suggest like always you look at the key article, what was their goal, what they are targeted, why they have used that amount of mixing. Then that will give you a, because in density functional theory, formalism, everything is fine. All Sir was talking about, everything is basically in the Pardue's Jew. Over the last, 40, 50 years, more than 50 years, right? People have been, what they have been doing? That exchange correlation, right? Keep on adding, and sometimes students, when I was a student, I was clueless what to do. You get a suggestion, oh, use this one, okay, right? But when you use this one, you go back and go, why it was suggested by your professor or senior or someone else, and then you will get a lot of information. Although it takes time, but it is worth putting that effort. Okay, coming back to this is basically what Professor Manoj Harballa was referring. DFT, if you have an exact theory that negative of homo-orbital energy should be equal to IP. So this is something, if any class of functional is following this one, this condition, we call Koopman's compliance class of functional. Okay. So this is basically a DFT analog of Koopman's theorem. I am saying DFT analog of Koopman's theorem. The reason is that Koopman's theorem true for all the orbitals Professor Pothim Chattaraj were referring. It's not just for HOMO, it's for all orbitals, right? There is no orbital relaxation. But here we have orbital relaxation and we have just for the HOMO. And he was also referring the Yanak's theorem, which takes care of the partial differentiation of the total energy with respect to the occupation of a quantum orbital is going to be equal to exactly the quantum orbital energies, right? You can show this one, this ionization potential theorem or DFT analog Koopman's theorem. If you satisfy this one, how do you satisfy? You ensure by choosing that pointer gamma in such a way that you get. So here is basically I am saying this gap tuning or RSH tuning. What you do, you define a error function, like you are minimizing this error, deviation of IP from the HOMO energy. See, our DFT ground state energy is good. So you can calculate the IP from ground state energy, which is known as delta SCA method. If you have a cation energy, neutral energy, you get the IP and you force this error function to be as minimum. Essentially, I should get 0, but numerically you will be not able to get 0, right? But close to 0. And then you say that pair of alpha and gamma, or simultaneously you can tune. We call this a two-dimensional tuning, right? Alpha and gamma simultaneously you tune and get an optimum value for your system. So here is
Separated functionals, you are bringing in error function.
yes.
Okay, specific definition.
This is error measure. I'm sorry, error estimate. Okay, this is basically deviation of HOMO level from the ionization. What you need, because some of you are thinking, sir, why should I worry about IP? If I have to get IP, I will just do total energy of a cation minus total energy of neutral, right? Okay, that is the delta SCF well established. You don't need to worry about the eigenvalues. But if you are having a periodic systems, okay, the problem comes, right? Because our goal is not just IP and EA. Our goal is basically get the quasi-particle spectrum rightly captured, right? So if you minimize this error measure or error estimate, for each molecule you can calculate. So it has been shown. This is basically a tetrapyrrolic. This is a porphyrin derivative. You see, this is basically that. What is this JN? JN means what you are doing. You are applying, enforcing Koopman's theorem for the neutral system, right? Because Koopman's theorem holds true for any number of electron. So I have Koopman's theorem satisfied for the neutral. I get my HOMO level corrected. Now what to do with the LUMO? Because those are coming with a Lagrange multiplier. There is no physical significance of all those LUMO, LUMO plus 1, etc. Right? So what do I do? Then you add one electron, make the system like anion, and then HOMO of the anion is essentially going to be LUMO of the neutral, and that's how you know align them. HOMO and LUMO, you align them. So in this error function, if you look at this is sum over n and n plus 1. Okay, and if you minimize, if you see the value of that pointer is basically 0.16 Bohr inverse. For the default, depending on the quantum chemistry code that you use, it will be like 0.33 or 0.25 or 0.2, right? But for this system, that value is not optimized. But this is just a static DFT calculation without almost zero cost, additional cost, right? Still, so you can get access to this pointer, right? And then you have a right functional for your systems. So this is called system specific tuning, is known in the literature optimal tuning. Okay. Now this is, you see some studies I have brought, the experimental ionization energies versus HOMO energy. As Sarah was referring, if you are using DFT, LDA, GGA, HOMO will be highly underestimated, right? If you are having FOC, then it will be overestimated. Yeah. Yeah, because at the end of the day, I am interested at HOMO level. That is my ionization energy should be. LUMO is basically some electron affinity, right? And if I have a photo excitation at the two level system, so HOMO to LUMO excitation. If HOMO is fixed, LUMO is not fixed. So still I will be having a problem with my optical excitations. If my functional is able to take care of the derivative discontinuity well, so fundamental gap is going to be HOMO-LUMO gap. Okay, the derivative discontinuity has to be taken care by your exchange correlation energy, exchange correlation potential. Then I will be having exactly the HOMO-LUMO gap, what we refer electronic gap from. Once again, could you repeat? Now that's what I'm saying. If you have an exact, let's say you have an exact functional, okay, we don't know it's exact functional. So that time that fundamental gap IP minus EA or IP plus EA, whatever I have wave, it should be equal to the HOMO minus LUMO, LUMO minus HOMO, or whatever that magnitude, that gap. Why not? Because the derivative discontinuity is, because the whatever the differences comes, the derivative discontinuity. If I am able to take care of that well, so my electronic gap in principle should be equal to that IP plus EA. But because that is taken care. That is all because I will be having a this piecewise linearity condition satisfied.
Even the exact exchange correlation function will not have the derivative discontinuity until it has a very strong independence. And that independence function is not if it is a purely dependent on density, even if you make it exactly,
I see.
that is a big problem. So what the latest is that, and there are many papers on that we want to get the band gap right comes out correctly if you have the generalized KS. And generalized KS means truly generalized, does not mean just the Hartree form, but any exchange correlation functional that has phi dependent. That's why meta GGA has become very useful, because in meta GGA you have these functionals which are phi dependent through the kinetic energy. And when
you mean to say hybrid meta GGA, right?
No, even the regular meta GGA like scan.
But you don't.
Scan would have a dependence on phi. If you calculate the exchange correlation for potential for scan, it depends on the ith orbital. Now what happens is, if you do that, then the orbital for the valence orbital, the potential will be something else, for the other orbital will be something else. They're treated differently, and your band gap comes out to be all right. The moment you make it local, suppose through optimized potential something, then the band gap just becomes half.
I see.
So this is a lot of development. Those of you who are interested, there have been papers. 2 years ago, there was a paper in PRB where they inverted the exact the Monte Carlo density of solids, got the exact exchange correlation potential, and calculated the gap. It was 1/2 of the two gap. Recently, also in PRB, I think it appears soon.
I see.
There's another paper that has done exactly the same. So even in exact cone-sham potential, your band gap would never come out. So generalized cone-sham gives you band gap.
No, that's why whatever the context I am defining, everything within the generalized construct. That Seidel, 1996.
So necessarily you have for the band gaps, the two orbitals are being treated separately.
Yeah, that's true. And what we have, that orbital dependent, that operator is sitting in my constant. So that's why that IP will be necessarily equal to that negative of homo energy, and electron affinity is also going to be equal to the negative. Exactly. So that is how.
You see, the majority of the correlation, conduction band, the orbital, it is concentrated somewhere else, valence is come. So if you have potential has that kind of dependence, it automatically shifts.
Yeah. And that is what being done here actually. Exactly. Okay, yeah. So here is basically. Yeah.
That, because when you do the actual self-consistent field calculation,
relaxation effect is there.
You have information only about the occupied orbitals because your density is calculated using that.
True.
So that's why it is called that the partial orbitals are garbage of any self-consistent field calculation. Now, giving too much of importance to LUMO and other higher energy orbital is a bit risky. I mean, whatever exact calculation in self-consistent field calculation, because you were giving input of only the occupied orbital.
So
your density never.
That's true. I mean, it's only occupied.
Of, let's say, LUMO or
Yeah. It's sum over up to occupied. Yeah.
What you're doing, you're calculating electron affinity and the band gap. So there you should be a little bit careful that.
Now I understand that this is Lagrange multipliers, and also what is being done here, it's basically to capture the LUMO. You add an electron to the system. You make it n+1 systems. Okay.
That is the
common technique here. So that.
There should be some semblance that you are doing with.
Yeah. So that is how you are capturing this band gap actually. Yeah. 5 minutes. Okay. So yeah, this you see, I mean, this is probably, I will not, these are all, OPV or organic photovoltaics related molecule where, the homo level alignment. If you see that experimental data and optimally tuned functional GW, they are aligning linearly with the experimental, but B3 leaf, even if you have a, fork-like exchange within GKS, their values are, highly underestimated. This is just to showcase this one. And this is basically not only the band gap. You look at this molecule, the band gap with PB, probably this is well known to all of you, 1.8, which is just a homolumo excitation. Optical gap, if you look at 2.1, this is like a garbage. You can't have the optical gap more than the band gap, okay, or fundamental gap. So this is PB is giving a garbage data, and you look at that B3 leaf. It's okay. B3 leaf is giving you reasonably, good optical excitons. That reason is that because of
this is what is called right reason for
wrong reason. So You don't have the elongation of the stretching of the gap, and top of that you are not having the electron hole, the interaction captured well. So they just cancel out. So you have a right result for wrong reason in the literature it's referred, right? So this is just to showcase we have pi star type of excitons. So B3 leaf, whoever is doing an experimental calling, they get okay, my spectrum match with the experimental nicely well. That's why B3 leaf has been chosen. But you have the right result for wrong reason. Okay, but here in the range separated scheme, you have the right result for the right spirit. The B3 and the optical gap. This is the B3 leaf gap 2.8. This is the homolumo gap, but this homolumo gap is going to be equal to that fundamental gap. So this is from linear response to DFT. This is the excitonic. That's kernel has to be calculated. ES goes down. So electron hole exciton binding energy is captured. Okay. Yeah. Now here particularly for this molecule you have, if you look at that particular, that is basically the 100% contribution to HOMO to LUMO, particularly for this molecule. You can have an excited states, you may have the combinations of multiple configuration, but this is like a HOMO-LUMO excitation. That's why I am able to connect like fundamental gap with optical gap, right? It has to be like a two-level picture. I hope you have understood the Professor Soman's questions, right? So as long as I have HOMO-LUMO, I can talk about. But if I have some excited state also is other occupied unoccupied pair is contributing, that correspondence this doesn't make sense. Okay. Next one is basically this is a charge transfer excitons. If you look at this is basically like you have excite. This is a molecule like zinc porphyrin linked with porphyrin via a phenyl ring, and phenyl is placed orthogonally. So you have a clean charge transfer state. If you look at the B3 leaf like a CT states, you look at CT states energy is highly underestimated. Okay, and this underestimated energy is mapping with the experiment. The reason is that you have not captured the dielectric effect of the medium, and the charge transfer states already in the gas phase, whatever you are getting is matching with the experiment. But reality in vacuum, your charge transfer state energies is quite high, and whatever the stabilization of CT states is due to the solvent dielectric, it has to be. So this is just to showcase like the CT excitons, you need this kind of long range corrected functional if you are not able to do GWBSE. Okay. And this is another one example of non-covalently bound donor acceptor complex, how accurately, I mean reasonably accurately captured the CT excitons with OTRSH. And I think I have to stop, right? I think this is the part something anyway I'll discuss because you'll be doing some hands-on, and that hands-on will be based on this concept actually. Maybe I'll discuss there. Okay, I'll stop here. Sorry, I have taken
So the lab session starts immediately after the tea break, or because I don't see the tea break here.
I see. So sorry, I could not talk about the range separation of other class
10 minutes.
Where we do also range separation for the correlation.
Tea.
It's okay.
Okay. Yeah, if you take.
So I'll do one thing. This is in the lab session. Maybe I'll discuss. This is what is basically whether this range separation scheme you are able to capture the low lying charge transfer state well. But in addition to the low line charge transfer state, if you have a multi-donor, multi-acceptor type of system, you may have like CT1, CT2, CT3, right? How do you do that? Actually, for that, what we refer like a state-specific optimal tuning, okay? So this I will discuss in the lab session on board, it will be clear. But quickly, I will just range separation for, this is what one interesting, like if you have a solid state, like a pentacene in a crystal. So if you do GWBSE, you get the dielectric matrix. But instead of that, if I can have a scalar dielectric constant of the systems, my long range potential should be scaled by that scalar dielectric. Although this is an approximation because I don't have a full inhomogeneous dielectric matrix. So this is basically called screen range separated hybrid. This is the work with Lior. So where the screen range separated hybrid is shown able to capture really well with respect to the GWBSE. Okay, the screening is where? Screening is added in the long range part of the fork like that exchange potential. Okay. And these are all some data, and this is one system probably Professor Somen will be also interested. This is what I wanted. Can you also think of range separation for the double hybrid? I mean, you can think of, but do I need to do that? So some systems, like this is a tiny molecule, heptagen, is a classic example where we violate the Hund's rule. What is the Hund's rule? Is basically the triplet will be lower in energy than the singlet excited state because you have a exchange driven stabilization, right? So this is the Hund's rule of, for triplet low lying, right? But here you see is the other way around. It's like a triplet is higher, singlet is lower. And people have, identified some possible reason why you are having this kind of inversion. The normal case, triplet supposed to be here, okay? But in this case, it's an inverted picture, and people have identified, okay, if your singlet is having spin polarized, spin killing is important, or double excitation character, or if you have some kind of dynamic correlation that has not been captured by your DFT correlation. So you should think about, addressing some of the issues here. And the exchange is essentially this homolumo. If you take the overlap, that is the exchange. If you have a complementary homolumo, exchange is going to be close to 0. And if exchange is going to be close to 0, the S1 and T1 is going to be degenerate. But on top of that, you have a double excitation character to S1. That's why you are having slightly below. And there are a lot of, literature last 2-3 years, if you see whether this is an artifact of the theory or this is because experiment, they don't have this heptagen isolated. They have a derivative of heptagen, has been shown like this TADF, reverse intersystem crossing, is like a very high yield, okay. So here, you look at this, I talked about this tune functional also not able to capture that inversion. I think in the previous slide I have given, if you look at the singlet triplet gap is about 0.2 with the twin functional, where triplet is lower in energy. Whereas the CC3 couple cluster, the order 3 is giving you the minus 0.22 electron volt, the inverted gap. So OTRS is not able to do. So there it comes, can we go one more rung? Because if you look at the reason, what you are having some kind of double excitation dynamic correlation. So that is giving you some hints like in quantum picture or Hartree-Fock picture, we have a localized picture, right? You need to just allow the electron cloud to also move to the virtual orbitals, right? And what is the foundation of that MP2, molar placet perturbation theory of second order, right? So there what you are having some kind of double excitations captured in terms of correlation energy, because singles cannot give because of Billion's theorem, right? Slater-Condon rule says only the double excitations contribute, right? So that MP2 correlation is essentially taking into account some amount of dynamic correlation in addition to the double excitation character. So if you are adding that MP2 type of correlation, I'll directly go, this is basically the spirit of double hybrid. This is a global double hybrid. What you do, some amount of Fock exchange or Fock-like exchange, okay, mixed with complementary amount of DFT exchange, and then earlier the full correlation was, I think these two terms, one will be the DFT correlation, another one will be MP2 correlation. There is a typo, okay. So this is a global. People have done this one for non-covalent interaction, okay, and reaction barrier height, like activation barrier, people have done this density functional for the activation barrier calculation and non-covalent interaction also. Because you have MP2 type correlation, this is itself is a non-local. Now in the range separation answers, if you look at what you have, this term, this some amount of Fock exchange in the short range, and then complementary of DFT, exactly like that range separation scheme I discussed, right? Then since the correlation importance is less, Sarah was talking about correlation plays less role than the exchange. So this particular in this author, so this is like if you take the square of this, that will be like if you have a 0.2, it will become like 0.04. Like some amount of MP2 type correlation you add in the short range, and then complementary amount of DFT correlation you put it in the short range. And then you can have MP2 correlation in the long range. Full MP2 correlation you put long range, and then this additional correction term is here. The reason is that we have MP2 correlation which is non-linear in Coulomb potential. Okay, it is not linear kind of things, it is non-linear. So you have to have this kind of mixing term, and this can be easily evaluated if you calculate MP2 correlation energy for entire range and then short range and long range, that interface corrections you will be able to get it. And here you see this is a standard, if you look at the JAVO quantum chemistry, modern quantum, chemistry books, you will find this how you calculate the MP2 correlation energy, right? So this essence is that if you look at, this is a kind of double excitation in terms of correlation it is entering. If you are able to do that for heptazine, you see you are qualitatively able to get the inversion, okay? Not quantitative map, the qualitatively you are able to get, where OTRS was giving 0.19 electron volt, other way around. But this is with 27% of MP2 correlation, right? So then we look at, okay, what will be the impact of omega variation, with a fixed MP2 correlation? We see there is no impact. If you change the pointer, is essentially this singlet and triplet, the energies are degenerate. There is no, they are essentially because the exchange energy is 0. Anyhow, exchange is not there, both the states are 0. But here at a fixed value of omega, if you vary the MP2 core amount, so you see in this region around 35 to 45, you are able to capture not only the qualitatively, almost quantitatively you are able to capture. And the quantitative, when I am saying this is comparing to CC3, the gold standard method, couple cluster of the order 3. Okay. So that means this MP2 type correlation, which essentially comes like a cis with perturbative double correction type of correlation, is included into the exchange correlation potential. You are able to get this inverted picture captured for the excited states. And they are all some systems, and I think this is fine. I think I'll stop here. Okay, I'll stop here. Yeah. Thank you all.
Any questions probably during the tree break would be better.
Yeah. Sorry about, I think.
So then break for tea and then.
So this is the problem. It's a very simple problem you are going to test in the hands-on. You choose any molecule, like benzene molecule, try to calculate IP using PB, which is semi-local functional, B3 leaf, global hybrid, and then range separated hybrid. See which one is giving very close to the experimental value. This is first problem you look at. And another one problem, this implementation of this OTRS is important for the charge transfer states. Okay, look at like how does the charge transfer state energies vary with respect to the distance from these three functional, and then you get a feeling like going from GGA to global hybrid to range separated hybrid, which one is giving you the correct picture, so that what you learn, you get a feeling of it. Okay, yeah.